Hi guys, welcome to our first video in chapter 22. Chapter 22 is the first in our two-part unit on organic chemistry, and we're going to start with discussing hydrocarbons. And so you can see the first lesson that we're going to talk about is hydrocarbons, and we're going to introduce them. Okay, so over the course of this unit, we are going to compare the structure and properties of three things called alkanes, alkenes, and alkynes, which sound similar and look somewhat similar, but there's some key differences. We're going to recognize and compare the properties of structural isomers and stereoisomers. And finally, we're going to describe how useful hydrocarbons can be when obtained from natural resources. Okay. So I just have three images here. We've got organic chemistry, right? We have a picture of life here with the forest. Hydrocarbons are like petroleum. And so we have an oil well as well, three oil wells here. And then here's a sneak peek of what some of those alkanes are going to look like. And we'll start to see those in this video here. So let's jump right in with our first video, 22.1. And this first lesson is on things called alkanes. Okay, so we'll get to what those are defined as in just a moment. But I'd like to start by defining organic chemistry, right? Back in history, organic chemistry was really what chemists and alchemists considered to be the chemistry of life. And they thought that these chemicals were only made by living organisms, things like sugars, carbohydrates, alcohols, things that they could collect from originally living samples. This concept is called vitalism. Like vitalism is in like deriving from living things. Okay. We know that that is not true these days. We know that it is totally possible to synthesize organic compounds in labs. And that is actually the major way that organic compounds are made is through refinement or synthesis from petroleum products in labs. So we have a better and more generic term for organic chemistry. And the word organic compound is applied to all carbon-based compounds with the primary exceptions of carbon oxides like carbon dioxide, carbon monoxide. Those are not organic. Carbides, things like carbonic acid, right? And carbonates like sodium carbonate. Okay. These are not considered organic. They are considered inorganic. And we're not really going to talk about them in the organic chemistry context, but I want to draw your attention to the right side of the screen here. You can see that I have listed. I just have a picture that shows us many different types of organic chemistry groups. So there's those words alkane, alkene, and alkyne. And then we've got all kinds of what are called functional groups. That is actually going to be the focus of chapter 23, will be the functional groups. So for today, for this video, we're going to restrict ourselves to just introing what is a hydrocarbon. Okay, so hydrocarbons and alkanes. Now, to get right into it, right, a hydrocarbon is a compound that contains only hydrogen and carbon. Simple, right? These are the simplest organic compounds. There are thousands of these things. Carbon does this really cool thing where it can form bonds to itself. The result is that we can extend our chain of carbon as long as we want. Your average Teflon molecule has, let me look it up real quick. Your average Teflon molecule has got it has a repeating unit of two carbons and can end with trillions and trillions of carbon atoms in a single molecule. Okay, so we can have a lot of these things linked together. All right. Now, I have in this picture on the right-hand side a chemical you've likely heard of before called methane. And I have a couple of different ways of showing that thing. We have our molecular formula, our structural formula, ball and stick, and space filling model. But you can see this simplest of organic groups is a single carbon with four hydrogens attached to it. You can imagine if we wanted to add a carbon, we could simply replace a hydrogen with a carbon and then fill in that carbon with hydrogens, and we'd have another alkane. And we can go from there. We can keep going up from there, right? We take that, we actually see that right here. You can see what would happen if we add on a second carbon and then a third carbon. You can see it below. Okay, but I'm getting a little bit ahead of myself. So let's talk about our simplest type of hydrocarbons. That is called the straight chain alkane. And this is a pretty important vocab word. An alkane is a hydrocarbon that has only single bonds between its carbon atoms. Okay. I just said between atoms in that blurb, but it is actually in fact between carbon atoms because we can have double bonds attached, but to it, and it could still be an alkane. But between those carbons, it's only going to be single bonds. We call these types of molecules saturated because we have put as many hydrogens on our molecule as we can. If you look at some of these alkanes here I have on the right, you can see that our straight chain alkanes, these just have as many hydrogens on there as can fit. Okay. Now we can start, and I want to show you this table on the right-hand side. We start with methane. We go, and that's one carbon, CH4. We go to ethane. It's hard to see, but it is C2H6. Propane, C3H8. Butane is C4H10. And then we can go on. And if you notice, what's happening is each time I am adding a carbon and two hydrogens. I'm adding it on to the middle of my carbon chain. Now, this is all useful. This is all good. There is another way that chemists can represent this, and you've seen it before a couple of times. Let me make some space over here. But I want to show you guys another way that we could draw these things, and I'll start with propane. Okay, so we could draw propane as the C3, CH3, CH2, CH3 that we have there. But chemists are often trying to do this faster, and we'll use what's called the stick notation, or the straight line notation. So for this, we would draw a carbon, we would draw a line like that, where what we're trying to show is that at the end of the terminal end here, let me highlight it. At the end of my lines here, I have a CH3, and on a central carbon, I have a CH2. So I have CH3, CH2, CH2. To continue this, right, we can see the next one. To go to butane, I would have now an additional line on there. And again, what would I would have on each end? I would have a CH3, two CH3s, and then I have a CH2 in the middle and a CH2 in the middle here. So that's trying to redraw this in the same way. I can continue this, and you can see how fast it is. Like pentane's got 5 carbons. 1, 2, 3, 4, 5. And again, I have CH3 at each end, and I have a CH2 at each bend. And I could have chosen to draw this, like maybe let's draw butane. I could have also drawn butane slightly differently. I could have drawn it like this, over, and then down. That would be equally valid. And if I analyze this, right, I still have two ends, and they would each be CH3, and I have two middles, which would each be CH2. So these organic molecules have a little bit more freedom in how we can draw them. Like I could have drawn this pentane the same type of way, where I just have something like that. I can change the shape, but the zigzag is like the easiest way to do this. And I'm going to quickly draw hexane and heptane, octane, nonane, and decane. So you could just see how fast these really are. 1, 2, 3, 4, 6. Heptane. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So I got our hexane, heptane, and octane. I didn't do the nonane and decane, but you can see to draw these things, you just keep drawing zigzags. So be ready for that type of notation. You can also see that type of notation up here, where this alkane that's indicated in this diagram here has 1, 2, 3, 4, 5 carbons. So that means that this would be pentane. Okay, so that's another way of drawing these things. Now, speaking of pentane, the way we name these things is decently straightforward. We name them using a prefix followed by ane, for alkane. So the prefix, and then we do the ane at the end. So for example, you've heard of methane. I just mentioned pentane. We can have hexane. And the idea is that ane is always going to be true to tell us that it is an alkane. Okay. And then we use the prefix to tell us simply the number of carbons. So meth is the prefix for 1, eth for 2, prop for 3, but for 4. And you can actually find this in your reference table. There is a list of the organic prefixes that goes all the way down to decane. Okay. Now, the reason we don't need to talk about hydrogens is because our alkanes are saturated. So if we know, for example, that I have 2 carbons, well, I know that I'm going to have, I know that I will have something that looks like a sorry about that. My computer unplugged, but I got it fixed. So I'm gonna have something that looks like this, where I have a carbon bound to another carbon, and I know that it's saturated, which means I'm gonna fill my carbons with hydrogens. Each carbon needs four bonds. Since it's already bonded to one other carbon, that means each carbon is gonna get three hydrogens. And there we go. That is my ethane. Notice it matches exactly with the ethane that was given. So that's how we name and draw these compounds. Okay. Now, I mentioned earlier that the difference between all of these compounds, they're separated by just a repeating unit, right? A CH2. So if we look at all of these compounds in this table here, we'll notice that the CH2 is a repeating unit. Like this thing gets inserted into butane. We start with butane, we insert a CH2, and suddenly we are at pentane. That's now this guy in the middle here. We've inserted it in the middle. This is what is called a homologous series, right? Homologous series is a series of compounds that differ from one another by just a repeating unit. And we can go as far as we want with these homologous series. We are focused on alkanes. Notice that their structural formula is a saturated carbon, a hydrocarbon that is a carbon bound to another carbon, no double bonds, completely filled with hydrogens. This also gives you a little bit of the name where ethane, it tells you how to name it. And then very importantly, this also lets us predict formulas from names because we are given the general formula of CnH2n plus 2. So if my number of carbons is 4, like in butane, well, 4, so 4 carbons, 4 times 2 is 8, and then 8 plus 2 would be 10. So it should be C4H10. That's right there. That's exactly what we get for butane. So that's how you can determine the formula from these things as well. Another way you can determine the formula. Um, Now you can see sneak peek alkynes, alkenes and alkynes. We're going to get to those in the next two videos, okay? But before we go to those, I do want to talk about branched chain alkanes. So if we compare two substances that actually have the exact same formula and molecular mass, we can compare butane to something called isobutane, which actually has a different name that we'll give it. Both of them are C4H10. They actually do have meaningfully different boiling points. And so they're different species, and we need to be able to name these things, okay? And if you can imagine, the longer our molecule, the more options we have for branches that can become meaningful. So we need a way to name these branches. Now, those naming conventions require us to understand two concepts first, okay? First, the longest continuous part of a chain is called the parent chain. That's very important. And that's where we're going to start with this, is finding our parent chain. All branching groups are called a substituent groups, okay? And here's this little blurb here. Each alkane-based substituent group is named for the straight chain alkane having the same number of carbon atoms as the substituent, ending with the ane, replaced with the letters YL as shown in the right. So to simplify that, if I have this group here, this CH3 sticking off of the end, well, one carbon, that by itself would be methane. Okay, that would be called methane. But because now it's stuck onto another chain, we don't call it methane. We change that to methyl. So what we would name this thing, our parent chain, right? We've got the longest chain of 1, 2, 3 carbons. 3 carbons makes propane. So this thing would be base. The parent chain would be propane. And I noticed that on the second carbon, that middle carbon, so second carbon, I have a methyl group. So I'd call this 2-methyl propane. That would be the name of this isobutane. That would be another name of this thing. Okay. This would be the accepted name of this substance. Okay. But there is actually a pretty rigorous method of naming these things. So let's take a look at our IUPAC, the International Union of Pure and Applied Chemistry, IUPAC. That is the authority on chemistry in the world. Okay, so they've given us these naming conventions. And there's 6 steps. Number 1, count the number of carbon atoms in the largest continuous chain. Number 2, number each carbon in the parent chain. And we want to locate the end carbon closest to a substituent group. That is because we are going to number this so that the substituents are on the lowest numbers possible. Okay, and I'll show you what that means in our example. Next, we name each alkyl group substituent. The names of these groups are placed before the name of the parent chain. So we name the substituent groups first, then we name the parent chain. For if the same alkyl group occurs more than once, as it does in our example we're going to see, then we are to, as a branch off the parent structure, we use the prefix di, tri, tetra, etc. before its name to indicate how many times it appears. So this down here, this will be a dimethyl because I have two methyl groups here. So it would be dimethyl in my example. We'll get to it though. 5, when we have different alkyl groups attached to the same parent structure, place their names in alphabetical order. All right, so we're not just picking randomly. We are going to do this alphabetically in order to get to our naming convention, get to the correct naming convention. And then finally, step 6 asks us to write the entire name using hyphens to separate numbers from words and commas to separate numbers. Okay, no space is added between the substituent name and the name of the parent chain. So in my name here, right, it's going to say it's spelled wrong, but that's just because there should not be a space there. And notice I use dashes to separate the two from the number from the letters. Okay. Before I do the example, I want to show you guys some very common alkyl groups that are usually substituents. We have our methyl group, that's a CH3. We have ethyl, that is CH2. So, oh, look, there's an ethyl group. We have propyl, which is a CH3, a C3 group. We have isopropyl. And notice these are both propyl. They both have 3 carbons, but this propyl group is attached to a terminal carbon, whereas in this isopropyl, a central carbon is attached to my chain. So they look different. They're going to act different. Okay, they are in fact meaningfully different. So I would like to now go through this example of how I name this branched chain alkane. Now I need to start by numbering this thing. Okay, numbering the parent chain. I can see clearly if I count this right, 1, 2, 3, 4, 5, 6, 7, 8. I can see that I have 8 carbons there. Cool. If I were to try to go up and count this thing up, right? 1, 1, 2, 3, 4, 5, 6, going up this ethyl group here, that would not be that would be 6 carbons. So that's not our longest chain. So I'm gonna say this straight chain going across, that's our longest one. And I'm going to number this. I have 2 options now, and I'll do one in red and one in green here.
Can I have your attention, please? Will the seniors please head to the...
And notice that I have these 2 things numbered. I have 2 options to choose from, right? I started either what we'd normally start with for our so I have numbered our carbons so that each one has a unique number here that I can identify, and I can see that the red one goes from 1 to 8 and the green one goes from 8 to 1. If I were to choose this red one, my earliest carbon would come on, or my earliest substituent group would come on carbon 4, and my latest group would come on number 5, or sorry, number 6. If I compare that to my green numbering, I can see that my earliest substituent here would come on carbon 3. Okay, so because the green numbers put my substituents at a lower number, we are in fact going to go with the green numbers. Okay, so let's start naming this thing. Now I can see that I have 8 carbons, so that is going to be, if I scroll up, that will be an octane, octane. Okay, so I've got an octane, but I also know that I have two types of substituent groups, right? I have an ethyl group up here. I have 2 CH. Sorry, I have 2 carbons in a chain, and then I have 2 methyl groups down here, okay? So my ethyl group is going to get named first because E comes before M alphabetically. And so I'm going to name this thing. It comes off of the 4 carbons, so we can see that we have 4 ethyl, right? So we're going to have a 4 ethyl, separated with a dash, ethyl, 4 ethyl, and then I'm going to say dash because now I've got to give my methyl groups. And I have a methyl group on 3 and a methyl group on 5. So I'll say 3, comma 5. Dimethyl. Di because I have 2 methyls. All right, so I have 1, 3, sorry, I have 4 ethyl, 3, 5 dimethyl, and then this thing is octane, octane, okay? So 4 ethyl, 3, 5 dimethyl octane. And that is the name of my substance here. All right, guys, that's all I have for this video. Thank you for listening. I'll see you in the next one.